And let me know, you should be seeing one full screen title slide.
Yes.
Great.
We are recording, so proceed.
Okay. Well, thank you all so much for joining us this evening and for giving me an opportunity to speak to this group. Again, I know so many of you and definitely miss Michigan. And although I'm also having a great time out here in Colorado, so it's all good. And today I get a chance to talk about lightning, which, I mean, let's be fair, it's just a fun topic to talk about. When I was at NASA Johnson Space Center, I got a chance to do some lightning research specifically with how it impacted pyrotechnic systems and the little NASA standard initiator electroexplosive devices that are pretty ubiquitous in NASA programs. And then when I was working at Ford, obviously lightning wasn't quite as much of a top of mind concern. But now that I've joined EMA out here in Denver, it's definitely something that is core to a lot of what we do. So I want to talk today about sort of lightning in general, how aircraft interact with it. We'll talk a little bit about spacecraft as well, and then how both simulation and test feed into making sure that aircraft are safe. And when they get hit by lightning, which is more often than you think, they don't fall out of the sky. So I want to start by talking a little bit about just, in general, the lightning threat. It's an amazing natural phenomena, but it does present, tremendous risk. And you can see along the bottom here, an aircraft that that actually had a hole punched in the fuselage based on lightning strike. In the middle, I'm not sure how many people in this community know it, but Apollo 12 actually got hit by lightning on launch. So while it was in the air during its launch phase, it was hit by lightning. Luckily, because the Apollo capsules were basically metal, they hadn't switched yet to the lighter weight composites. The whole thing was able to keep flying. So all the electronics flashed red. They lost communication with Houston briefly, but they were able to reestablish everything while they were still on their way up. So that was, that was a pretty lucky day in the grand scheme of the history of the Apollo program. And then you can also see, obviously, stationary targets. There's a reason buildings need lightning rods, and you can see what happens when wind turbines get hit. So as wind power becomes more of a thing, that's something that has to be taken into account as well. And when lightning strikes an object, obviously there are tremendous physical forces from, thermal forces, acoustic, but also the electromagnetic forces that come into play. And then there's the direct effects, like what you see on the aircraft, heating, having holes punched in things, warping from electromagnetic effects. But then there's also the indirect effects. So that's the results that get induced on, for instance, cables. So as whether an aircraft takes a direct strike or just a nearby strike, the electromagnetic fields are going to impact the cabling all through a vehicle. And that's also something that needs to be taken into account. So taking all of this into account, whether it's protecting people in aircraft or protecting monetary investments into things like wind turbines, analyzing lightning, protecting against lightning, it's all very important part of the sort of subgenre of electromagnetic environments.
Sure.
Now, it would be criminal not to have some good video of lightning. So that's an A380 that's coming in for landing. You can see that it's landing gears down. And then obviously it takes that strike, but because these things are extremely carefully designed, they were totally fine. Everybody on board was fine. It landed fine, no problem. Another person who probably feels pretty lucky is the pilot of this particular fighter jet who took a direct strike. And again, a shocking occurrence, but totally fine. Aircraft stayed in the sky, pilot was fine, because of the engineering that goes into protecting these kind of things. And we'll talk a little bit later in the slides about some of the history before these kind of protections were put in place. So just in a very high level, what is lightning? I know most of the people in this audience already know. So lightning's caused by charge separation, and that can be from cloud to cloud or cloud to ground. The clouds essentially act as charge reservoirs, and then when that charge gets unbalanced, it has to re-equalize. So the way lightning ends up manifesting itself, and in the very next slide, we've got a really nice, super slow motion video of exactly how this works. So you start to get this stepped leader that's not carrying that much current, but a lot of voltage starts to come down from the ground. And of course, we're talking cloud to ground at this point. As all these different branches start to find their way close to the ground, there's going to be an upward leader that comes up. And once the upward leader meets one branch of the stepped leader, then essentially the circuit's complete, and the return stroke is the part that we usually think of as the lightning stroke. So that's where most of the energy is contained. It can, have thousands to hundreds of thousands of kiloamps of current. And it's interesting, it's not that fast. So in the video that we'll see next, you can actually see all this develop. It's much slower than the actual speed of light. But then there's potential for multiple return strokes as the charge balances itself. And right, so let's take a look at the slow-mo video. See if I can make this work. Yes. So you can see the start, and then the leaders start coming down, and towards the bottom left center is where it's going to get close to the ground. You can see it's all still branching out. Take a close look. There's going to be a leader that comes up, and then the full return stroke hits. So if we can watch that one more time, now that you know where to look. So the stepped leaders go out. They're reaching for the ground. Once one of the branches gets close enough to the ground, an upward leader manifests itself, and then all the charge gets dumped in the return stroke. Now, I don't know how many folks have seen this, but you can essentially make the same thing happen in almost any medium. And you can make some amazing wood art if you have a couple of nails. So they've driven nails into each corner of this wet block of wood, and then just driven immense amounts of voltage between the two points. And you start to form what you call Lichtenberg figures. As and again, it's the exact same phenomena of trying to get electrical current through what's normally an insulator because the voltage is so high. So as they're reaching for each other to try and complete the circuit, they form exactly the same kind of patterns that you see from stepped leaders in lightning in the sky. Just in this case, they leave a beautiful permanent record of it.
Hey, Karen, can I ask a question?
Sure.
Yeah, I have seen this kind of lightning start seems always from the cloud and strike the ground. Why I haven't seen the other way, the lightning start from the ground and go to the cloud?
That is a good question. It can happen both ways, but I believe that well, of course, cloud to cloud lightning is actually the most common. And then it's cloud to ground. And I would need to reread the relevant section of lightning protection of aircraft to remember why it's almost always top down instead of bottom up.
Yeah, that's something we have been seeing, all the time. I have never seen one started from the ground.
Right.
Okay, thank you.
So here's another just great picture that happened to actually capture an upward going leader. And another one that just shows, again, essentially the cloud being the charge reservoir and dumping all that from cloud to ground. And again, just a stunningly gorgeous picture. And then, as we mentioned, most lightning is actually cloud to cloud. Cloud to ground is a little bit rarer, even though it's what we tend to think of, because that's where we tend to get damage to structures, buildings, that kind of thing. But the most amazing lightning stroke that I personally ever saw, I was living in Houston at Johnson Space Center and going across one of the bridges to Galveston Island. And as I was getting towards the top of the bridge, I was lucky enough to spot a cloud-to-cloud strike that was actually a helix. So it actually spiraled, corkscrewed from one cloud to the other cloud, and then hit the full return stroke. Uh, I will never capture something like that on camera because you just have to be too lucky, but it was really a sight to see. Now, again, all those pictures that we just showed, those are, very classic. There's a thunder cloud and the lightning is either going cloud to cloud or from the cloud right down to the ground. But lightning can actually travel quite a fair ways away from its, the thundercloud that you could think of as spawning it, or it can manifest itself in an area that doesn't look cloudy to us. And so here you can see a lightning stroke that just happened to have a long horizontal component before it actually arced down and found its ground path. Pilots have reported getting hit by quote unquote in the clear strikes as much as 25 nautical miles away from the actual thunderheads that they were routing around to try and avoid. And again, talking to pilots and there are agencies that actually compile databases of lightning strikes to aircraft as part of a multi-decade research effort. That kind of in the clear, or what they could sometimes call blue sky lightning, can happen as often as 1 in 100,000 flight hours. So just because you've routed around the thundercloud doesn't mean that you've completely avoided any risk of lightning. A few more great statistics. So in terms of a design environment, what we usually use is the 1% peak current. So roughly 1% of all lightning strikes will get up to 200 kiloamps of current. And so that's a value that we can all design against. And certainly when I am evaluating spacecraft, that's the number that we tend to use. The largest measured stroke was measured in the Sea of Japan, actually, and it was 450 kiloamps of current, which is just a stunningly large number. How many restrikes you can have in one flash can be up to into the 20s. And then here's an interesting thing. 90% of the lightning strikes that airplanes encounter are actually triggered. So they're triggered by the presence of the aircraft, and we'll talk a little bit more about that. But it's triggered lightning instead of natural lightning, in that if the aircraft weren't there, the lightning strike probably would not have happened. So talking a little bit more about specifically how aircraft interact with the lightning environment. Early in the history of aviation, I'm hoping that most hot air balloonists probably thought twice before taking off into thunderstorms. So I don't know of any hot air balloons that got hit by lightning. But in 1915, during World War I, this particular German Zeppelin, which is not the Hindenburg, as soon as I showed my husband these slides, he was like, the Hindenburg. I was like, no, there were more Zeppelins than just the Hindenburg. But this one, it was ferrying war material for the German effort in World War I, and it unfortunately went down due to a lightning strike. And in 1929, a Ford tri-motor called the City of San Francisco was flying in a thunderstorm, got hit by lightning, and ended up crashing into Mount Taylor near New Mexico. And in both cases, it was all hands lost. So very early on, the risk was certainly noticed, and people started to develop approaches, crude at first, but obviously much more refined now, to make sure that aircraft would be robust against lightning. One of my favorite parts of the book Lightning Protection of Aircraft comes from some early research efforts where they interviewed pilots, and they just asked, if you feel like you're flying in a region where you might encounter lightning, what strategies do you use to avoid it? And a lot of people had the same kind of idea, climb or descend through the freezing level as quickly as possible. And we'll find out a little bit later that that's not actually bad advice. They just didn't quite know. They kind of equated the temperature with the lightning risk. Another one, avoid all precipitation. Just anytime there's rain, snow, anything, just fly around it. Don't get anywhere near it. Slow down to a minimum safe speed. Change altitude to avoid a temperature of -7°C to 2°C. Again, somebody felt like they had that just really well dialed in. But here's my favorite. Lead a clean life. You know, sometimes that's the best you can hope for. But you know, with apologies to all these folks, we've got a lot better understanding now, both of what the lightning threat really is and how to protect aircraft against it, so that you don't have to worry quite so much about whether or not you've led a clean life. When it comes to, so we've already talked a little bit about, there are two major effects that we have to worry about when we're thinking about how does lightning interact with aircraft, and they're the direct effects. So when a lightning takes a direct attachment from a lightning stroke, or when aircraft takes direct attachment. And so that can involve melting or burning of components, flat out destruction of components, magnetic force events, acoustic shock waves, arcing and sparking, and that's especially a risk around bonds, hinges, and joints, because the impedance to the lightning current flowing changes so much at those areas. And then especially the ignition of vapor within fuel tanks. So generally speaking, the fuel tanks in an aircraft are held out in the wings. So most of the wings are full of fuel. And a very common, and we'll see from lightning zoning in a little bit, very common attachment points are a lightning strike that attaches at one wingtip, travels from wing to wing, and then detaches from the other wingtip. So if, you know, as those currents are redistributing from wingtip to wingtip, if they encounter higher resistant or higher impedance bonds where all of a sudden they start dumping more energy and potentially start arcing or sparking, if that were to happen within the fuel tank area, that could be a very catastrophic day. So that's one place where, you know, where we're going to spend a lot of time and attention to make sure that that can't happen. And then similarly, indirect effects, as those currents are redistributing around the fuselage, around the outer skin of the airplane. And again, this is true whether the airplane's taken a direct strike or just a nearby lightning stroke. The you know, there will be currents induced on the cables just because of the rapid changing electromagnetic fields in the vicinity. And we need to know how is that going to affect, you know, ultimately the conductors inside the cable harnesses and all the avionics boxes that are controlling the aircraft. Some examples of direct effect damage. Again, you know, fairly sobering pictures, places where holes get punched in things. This is an interesting one. So this particular aircraft has a composite frame or a composite skin instead of a metal one. So obviously it's got a higher resistance to electrical currents. And you can see not only has a hole punched through this, but it's also started to delaminate. So in a carbon composite stack up, you know, you have all these different layers, and in the presence of the very strong lightning currents, those layers can start to become disassociated. An example of magnetic warping over here. Again, components just coming apart. And then the nose of a lot of aircraft is not metal. It's actually a radome. It's something more like fiberglass, so that they can package a lot of sensors and antennas in that nose area. And the radome, you know, protects them from the aerodynamic forces, but still gives them an electrically clear path to, you know, see whatever they need to see of the sky. But that does mean that these radomes are a tasty candidate for lightning damage if they're not protected adequately. So again, you know, there's a big impedance mismatch between the non-conductive material out here and the conducted material of the fuselage. Indirect effects, obviously, it's a little bit harder to get pretty pictures of those, but just as we talked about, the cabling is definitely susceptible to picking up the transient fields caused by lightning. Lightning's a relatively slow phenomenon in a weird way. You know, for when you're used to thinking about signal integrity and talking about, you know, rise times in the nanoseconds, you know, lightning's really happening more in the micro to millisecond range. So the frequency content of it, usually what you're worried about is 200 to 400 megahertz and down. I know there was one time I was driving back from the EMC symposium in Washington, DC, and I was driving through Western Virginia and I hit just an amazing thunderstorm. And I tuned to an AM station. Pretty much I was thinking to get traffic information or road closures, and I could hear the lightning strikes on the radio. And basically I would hear it on the radio and then hear the thunder. And it's just because, you know, AM radio from 530 kilohertz to 1.3 megahertz is great at picking up lightning noise. And because RF travels much faster than sound, I could hear the lightning on the radio before I could hear it through the air. But all that is to say, that's the exact kind of frequency range that is great at coupling into cables that are many meters long. So we need to worry about the overall bundle, the currents that might flow in the bundle overall, and you can think of that sort of as the common mode current that's going to be induced. And then, you know, you're thinking about transfer impedances of how much is your shielding preventing or enabling that same energy to couple onto the conductors inside. And we're going to characterize that by open circuit voltage and short circuit current. And by evaluating how much of these quantities you end up getting on the interior conductors, you should be able to tell whether any of that is going to interrupt the electronics that, that are critical to keeping aircraft in the air. Now, how do we know some of this stuff? So God bless them, NASA outfitted an F-106 jet plane with just a whole suite of lightning monitoring systems, plus video cameras and cameras. And for 7 years, told the pilots to go fly it into thunderstorms. Which makes you wonder, if you're the pilot who gets that assignment, are you sitting there thinking, yes, I'm going to have a really exciting day? Or are you thinking, who did I piss off? But over the course of this research effort, that plane experienced more than 700 strikes. And that's how we know quite a bit of what we know about, you know, natural strikes versus triggered lightning. And here you can see a little bit more of its instrumentation. So multiple lightning sensors at all the normal attachment points, transient recorders, video cameras, different kinds of monitors. And then of course it was always tracked from the ground as well. So they were able to just develop reams upon reams of extremely valuable data from this kind of research effort. So it's always nice to remember that NASA is the National Air and Space. You know, it does quite a bit of environmental research as well as doing the outer space stuff. So what causes an aircraft to trigger lightning? So you've got these electric fields building up, and aircraft, just as they're flying normally through the sky, are building up a charge based on the friction between their skin and the air. So they're building up a charge, which is something they actually have to also bleed off when they land, so as to not be a shock hazard to the first person or the first piece of equipment to touch them. But so they're generating their own static electric field, and that's interacting with the overall electromagnetic fields in the, you know, the cloud kind of environment, the atmospheric environment. And then add to that the fact that sharp points or sharp bends of metal can cause electromagnetic fields to concentrate. So when you put all that together, that's one of the reasons why if an aircraft is flying through a region where maybe the fields have gotten to, you know, 200 volts per meter or something along those lines, that would not naturally be enough to trigger a lightning strike. But the aircraft flies through And because of either a sharp point out on, a tail or a wingtip, or the curvature of, again, the wing's leading edge, all of a sudden in that vicinity, the fields can get concentrated up to that, thousands of volts per meter that is much more likely to allow a lightning strike to occur. And so that's one of the ways that, that you can get triggered lightning from an aircraft interacting with the ambient electromagnetic environment. Now, this risk is not constant over an aircraft's entire flight profile. So according to research done by Boeing, and of course, obviously, researchers around the world are keeping an eye on this, keeping databases and records of this kind of thing, commercial aircraft experience a lightning roughly once every 3,000 to 3,500 hours. But almost no lightning occurs up at cruise altitudes. And the next slide will profile this a little bit more. Almost all the lightning that you're going to encounter in an aircraft, and just like we saw in that first video with the aircraft who was coming into land and already had its landing gear deployed, it happens at those intermediate altitudes. And so if you only count the time that aircraft spend in those altitudes, initial climb and then descent and approach, the chance of lightning actually go up to one strike in every 600 hours. So again, that just really emphasizes how important it is to make sure that lightning are adequately protected. Sorry, aircraft are adequately protected. Here you can see the distribution of lightning strikes per altitude. And again, the vast majority of it is happening between 5,000 feet altitude and 20,000 feet altitude. Once you get up to a normal passenger jet cruising altitude between 30,000 and 40,000 feet, then the lightning risk is almost non-existent. So for the vast majority of the time you're in the air, it's not something you need to worry about at all. But again, as you're taking your initial climb and then your final descent, that's when you're most likely to encounter the lightning environment. And it's the same thing for launch vehicles. It's when you've got spacecraft, there's the risk of usually indirect effects from having a spacecraft on the pad. If lightning strikes nearby, you need to be worried about how that's going to affect its cabling. And then you need to be worried again about either natural or triggered lightning during that first 20,000 feet of climbing. Here's another piece of statistics about natural versus triggered lightning, and this helps characterize the lightning threat a little bit more specifically. So natural lightning is less likely, but it is more likely to have a higher peak current, whereas triggered lightning is more likely, but is going to have typically a less severe peak current environment. So the nice thing about this is that if you design for the natural threat, which is more severe, then you've got a good amount of confidence that you're going to be fine when you get hit by the triggered lightning event, which is actually more common. Of course, it also depends on where you are. So you can see blue in this case is the most lightning that gets recorded. And boy, there's a lot of blue down there in Florida, right near Cape Kennedy, where so much of our spacecraft end up launching. And again, the pads are protected. They have catenary wires that help direct lightning away from spacecraft that might be sitting out there waiting for their launch window. But that does make a very challenging environment to launch into, given the frequency of especially afternoon thunderstorms in Florida in the summer. For those of you who remember back when shuttles were launching pretty routinely and also having their launches scrubbed pretty routinely because of lightning threats in the area, that explains that quite a bit. And I was actually a little surprised at how little lightning there is out on the West Coast. I grew up in Southern California, right around here. And now I know why I always think lightning storms are so special, because I really did not see very much of it when I was growing up. But since then, I lived in Houston, Texas, and that definitely gave me some good lightning shows. So when it comes time to take an aircraft through the certification process. This is an extremely high level overview of the steps. And that's because, you know, the details are going to vary whether you're trying to prove yourself to the FAA in America or the certification body in the EU or in China. But the overall approach is basically the same. So you're going to take your aircraft design, you know, basically the outer airframe, and you're going to establish lightning zones. So that's especially, pointing out where lightning attachment points are most likely, where lightning is likely to sweep through the fuselage. Then you're going to define the lightning environment for each of those zones and perform a lightning hazard assessment. So just like we talked about the fuel tanks and the wings, that's a place where you need to assess all the hazards based on lightning attachment points, lightning environments, what kind of severity you're expecting. And by the way, the lightning environment can also really be affected by if you have any flight constraints. For instance, if you said, I am literally only going to fly this vehicle in Alaska, you're looking at a very different certification than if you're saying, I want this aircraft to be able to fly anywhere in the world. So lightning hazard assessment, then you're going to go through and incorporate all the protection based on that lightning hazard assessment. So the mitigations that go along with making sure that each of those identified hazards won't actually damage the aircraft in a permanent or catastrophic way. Make sure that you've got acceptance criteria so that you can prove that those mitigations are appropriate. Verify compliance, and that's both using simulation and test, and then implement corrective action as needed. And in the course of this, obviously, you're going to be creating a stack of paperwork, you know, at least as long as the aircraft. So for testing purposes and for analysis purposes, we simplify the parts of a lightning stroke or a lightning event into that first return stroke, that's component A. That's a very short event lasting less than 500 microseconds, but it's where the vast majority of the energy and current occur. Then there's these two intermediate, component B and component C, which last longer. So B lasts up to 5 milliseconds and C can last up to a second, where you're getting much less current, but essentially that stroke is still hanging on to the aircraft. And then when you're talking about those multiple return strokes that can happen within one lightning event, that's going to be component D. So it also has quite a bit of energy, but less than component A. But we're going to, you know, this allows for standardization of testing efforts and what it is that you're going to actually subject all your different components to. Likewise, when we're looking at lightning zoning, this is an example of what that ends up looking like. So lightning zone 1A identifies regions where a lightning attachment is likely, but hang on is not necessarily likely. So you can see a lot of relatively benign curvature on leading edges are the kind of places where lightning might attach, but then immediately sweep. Lightning zone 1B, these are the much more sharply curved areas. In fact, there's one little blue dot at the tip of the tail, because that's the kind of place where lightning is not only likely to attach, it's likely to hang on. So you have to be prepared to endure a longer lightning event. Zones 1C and 2A are kind of places where those attachments are going to sweep. And then lightning zone 3 is places where it's very unlikely you're going to have a direct attachment at any point, but those areas are all going to be conducting currents as they redistribute themselves around the aircraft. Here you can see this is from one of the SAE guidance documents, that an example of sort of initial attachment, and then you're continuing to have direct contact with the lightning stroke. The stroke itself is stationary. It's really the fact that the aircraft is flying through it as it's delivering its energy. And then the same sort of analysis applies to the exit, to a detach point, or, you can consider that as another potential attachment point as well. So again, you've got this phenomenon where you have an initial attachment point, and then there are the places where you will still have direct contact just because of how the aircraft is moving through the lightning stroke. And over here, I just wanted to sort of illustrate how the same sort of lightning zoning analysis doesn't only apply to aircraft. Here are two different early variations on the Orion spacecraft and some of its lightning zoning. And you can see how it changes a little bit based on whether or not the capsule is encapsulated in a fairing, which offers it quite a bit more protection. But the launch abort system, so the LAS, that's this long thin tower at the top, that obviously has if anything's going to get hit by lightning, it kind of feels like the natural point where that's going to happen. So, I heard a really good talk from, well, just more of an aphorism from Andy Marvin last week. And he pointed out that simulation and test are like having 2 feet. If you only do testing, you're kind of hopping along on one foot. And if you only do simulation, you're kind of hopping along on the other foot. But if you use both, then you're much more likely to be able to walk in a nice way and get where you're going. So when you think about, if this is so critical, why not just test everything? Unfortunately, that still is pretty risky. Before you can test something, you have to build it. And you can only build, everybody's constrained by cost, right? You can only build so many prototypes. In this case, these pictures are prototype drones or, quadcopter kind of things that have gone in for some lightning testing. And then if you've gotten to the point where you're building prototypes, you've already sunk a lot of money into the design, into the manufacture. And if it turns out that your lightning protection scheme has failed, you end up having to completely redesign the system. And that's just that's a whole lot of money down the drain. The other thing is, more than your average electromagnetic environmental test, certainly more than say your normal radiated immunity test, lightning testing can be destructive. And so if you've totally fried something, like this example over here, this might be an example of a structural coupon with 3 good fasteners and 1 bad fastener, something that's been degraded probably intentionally in some way. And you can see this one started, arcing possibly to the point of ignition. If that were to happen in your fuel tank, obviously that would be a pretty bad day. But if you've brought this in for test and you've seen this behavior, if you want to try and threshold that, you're looking at having to build a whole ton more samples. And then, what if you have a different kind of fastener degradation, or what if one of the fasteners is completely missing? It's one thing to do that on a bunch of structural coupons that maybe measure 40 centimeters by 40 centimeters. Yeah, it's pretty easy to churn those out. But if you're talking about entire fuel tanks or fuselage sections, all of a sudden you don't want to have to build a bunch of those because you're frying one each time you test. That's just not feasible. So testing gives you a snapshot of one particular scenario, and obviously it's critical to have that, but it's very expensive to run multiple iterations. So if you can use the testing that you do and then make sure that anchors and grounds the 3D simulations that then allow you to explore many more aspects of sort of the design space, including different coupling mechanisms, direct effects, indirect effects, all different kinds of physical configurations, and also different electrical parameters. What if your transfer impedance has become degraded over time? Or what if we terminate our shields this way? Or what if we terminate our shields, with pigtails versus, 360-degree connectors? Or, what if we only terminate our shields on one end? You can ask all those questions without having to build all those prototypes. Model reuse, obviously, once you've put in the effort, you've got a good high fidelity model, then you can use it to answer multiple questions, because running a simulation thank goodness, doesn't destroy the model. So from there, you kind of work your way up. So I'm showing on the one hand, a big old fuselage section with the wings that's showing the current density mapping on exactly the kind of strike that we talked about earlier, wingtip to wingtip. But you can also talk about, this is one individual rib inside a wing. And this is experiencing essentially a lightning zone 2A kind of environment. This particular example, it looks a little pixelated, but that's because the software that EMA particularly uses for this kind of analysis is finite difference time domain based modeling. So that's going to discretize the entire space of the simulation. So it's going to mesh everything into these little cubes or Lego bricks essentially. And then it's a full wave solver. So it's going to solve Maxwell's equations in each space, for each time step where, the environment in one cube affects all of its neighbors, and you can, propagate Maxwell's equations and the entire electromagnetic fields through the space using that kind of simulation technique. So obviously, once you've done that, and you can make the mesh smaller for small components like an individual rib, or coarser when you're looking at something like an entire aircraft fuselage, but the concept's the same. And then depending on what frequencies you're interested in, again, you can mesh smaller or larger. Again, lightning tends to be on the low quote unquote, low end of the frequency range, being less than usually 500 megahertz or so. Or if you want higher fidelity, higher frequency content, this kind of approach is also really amenable to being run on parallel computing cores. So you can just throw more computer resources at it and get the answers that you need in, a relatively reasonable amount of time. Likewise, when you're bringing in the cable harness information, so for all those indirect effects, we want to know, again, so there's lightning currents flowing on the outside of the aircraft. How's that going to affect the cabling on the inside? So obviously, passenger aircraft have kilometers worth of cabling inside them, and the packing can get absolutely nuts in terms of, these bundles are literally multiple centimeters across. They've got dozens of different cables inside them with all different kinds of construction. So everything from twisted shielded pairs with their own shields, quadrax, coax, they'll all be shielded. And then you've got, overbraid shield around the entire thing. Understanding all the transfer impedances of that, there are a few different ways to bring all that into this kind of model. You can get, your wire and harness diagram. You can also import information from programs like KBL or the Zukin format. Then you can assign all that to the routing, which with any luck you've gotten from a CAD file of some kind. This one particularly was CATIA, but you can read in any number of different kinds of CAD files. Or you can use the ANSYS space claim interface to do all that routing if you have to do it yourself. And similarly, you can either pull in all your wire harness information, assign it to the branches in your cable routing, and have it sort of automatically generate, or you can use, again, the GUI through the CAD interface to specify all these cables, and give them all the properties that they should have. So your circuit terminations, shield terminations, impedances, transfer impedances, all that kind of stuff. So when you're building up to understanding the performance of the entire aircraft, there are a lot of different steps involved. One of the things is understanding the effect of impedances across different kinds of joints. So again, when you all of a sudden have a joint with an impedance discontinuity, that could look to lightning like a much higher impedance if you're unlucky, causing the lightning to dump a bunch of energy right in that area. and understanding, for instance, the difference between overlapping joints and butt joints, and then riveted joints versus, you know, other kinds of fasteners. That's the kind of coupon testing that then can feed into your model. Likewise, you can do all kinds of different transfer impedance measurements. This one's triaxial, to understand how different cable shielding arrangements are going to behave in these kind of environments. And then using that kind of information, pulling that into your simulation to make sure that you have this very high fidelity approach. Next, you can be looking at, you know, individual components or even subsystems. So here, starting to look at, you know, for instance, a fuel tank inside a wing, but just a section of it. This is something that's, you know, relatively easy to model, and also relatively easier to test. And so all of a sudden you can really start to make sure that your model is giving you the kind of information that you expect, and that it's lining up well with your test results. So in this case over here, the red line is perfect agreement between simulation and experimental values. The dashed line on the inside is agreement within 3 dB, and the solid line on the outside, that's agreement within 6 dB. And so that's, you know, so for this case, you've got basically agreement within 3 dB totally across the board for all the different cases. Then you can move all the way up to doing the same thing, but on the kind of full-scale aircraft model that only gets built once. So in this case, again, you know, modeling all the cables inside an aircraft, and then also being part of the testing effort where they injected this aircraft prototype with lightning representative waveforms. So that's very different than hitting it with an entire, you know, 200 kiloamp lightning strike. But same kind of plot results. You've got simulation values on the bottom, experimental values along the y-axis, and perfect agreement is the red line, then 3 dB, then 6 dB. In the vast majority of cases, even for something as complex as an Embraer passenger jet aircraft, you've got agreement within 6 dB almost across the entire suite of scenarios that were tested. And the nice thing about that is, if you've got the kind of aircraft where, say, you've got an MD-80 and that was certified and it's got thousands of flight hours or hundreds of thousands of flight hours, and, you know, it was tested as well as being simulated, and it's done well in actual, you know, fleet use. Now you're going to come out with an MD-90, which is, you know, basically the same aircraft with just a few changes. In this kind of case, when you have that history of excellent alignment between simulated data and test data from the component level all the way up to the full aircraft level, in that case, there are certain situations where certification for lightning could be allowed by simulation only, and you wouldn't have to build full aircraft tests. And that allows for savings of millions of dollars, you know, between not having to do everything that's required for a test, and then also not having to build that kind of aircraft prototype. Now, of course, that would not be allowed on a major, either a completely new aircraft or on an aircraft undergoing a major design change. So even if you had a perfectly good aircraft that had always performed well, did its full certification run, but you just decided to take its metal airframe and make it composite, but you're not changing anything else, I'm pretty sure that they would ask you to retest that. So when you do get to the full aircraft test level, it again, there's only a limited number of scenarios that you can test, but by injecting the basically scaled down lightning waveforms into, you know, different attachment points, and then using this series of return conductors to make sure that the currents may, as much as possible, keep an even distribution around the aircraft, you can still get this kind of this kind of overall understanding of how the aircraft as a full system is going to behave in a lightning environment, and then also if it's lining up well with the predictions from simulation and modeling. And the other nice thing, so that takes, you know, an aircraft all the way up to where it's being accepted by a certifying authority like the FAA. And the other nice thing is that once you've got a simulation program that has this full wave solver capability, there's no end to the different uses you can put it to. So in this case, what we're looking at is a fighter jet, and I believe this was built to evaluate the shielding effectiveness of its canopy. But this is looking at high intensity radiated fields and how they impinge on the vehicle. And again, you can see the really interesting effects at the wing tips as the plane wave impinges on the airframe. You can really see those kind of field concentrations that we mentioned earlier. Oh, and that reminds me of one thing that I meant to mention, which was why not do a lot of scale model testing? One of the reasons that you can't just build a lot of tiny scale models and go and test those for lightning, even though it would be much cheaper, is because some of these effects don't scale very well. So when you scale this whole thing down, you also scale down the bend radius, you make these kind of areas pointier than they would be in real life, you could end up over predicting the lightning threat. In this case, we're looking at how radiated fields bounce around a constrained environment. This is an example of a satellite that would be inside a launch vehicle fairing. It's turned on an S-band antenna that started radiating at 2.5 gigahertz. And the difference between these two situations, it's a little subtle, but there's a green sort of outline area at the edge of this bottom picture that doesn't exist in the top picture. In this case, the launch vehicle fairing added some acoustical absorbing foam, which usually wouldn't have any electromagnetic impact at all, but then it had a metallized layer on it. And so the question was, how would that change the fields that were bouncing around inside? And then also in this case, they included an umbilical cable from the satellite to the launch vehicle so that they could investigate how the fields bouncing around inside this fairing impacted on that umbilical cable. And again, we can expand this away from aircraft and spacecraft to, you know, the cars and the automotive vehicle universe. So we can either look at, you know, something like a CISPR-12 test, radiated emissions, you know, coming from the side, or a hood shot, or radiated immunity, your basic radiated immunity test where you've got, you know, plane waves that are impinging on your vehicle, and it's exactly the same concept, right? It's trying to figure out how that electromagnetic environment can affect the cabling inside the car. So it's essentially the same as indirect effects. That does it for my overall presentation. I'm happy to take any questions. If you think of any questions after, you know, later tonight or tomorrow, please feel free to email any of us. I know a lot of you know Dan Odom. He's our Vice President of Sales. We also have Cody Weber. He's one of our principal scientists too, who you know, has just immense amounts of experience with exactly these kind of testing and simulation efforts. But thank you again so much for giving me the opportunity to talk to you tonight. It's been a lot of fun, and I hope that you've enjoyed the presentation.
Thank you very much, Karen. That was very, very interesting. I really enjoyed it. Would you like to take some questions at this time?
I'd be happy to.
Okay. Anybody have any questions this evening?
Hi,
Karen.
Go ahead, please.
Oh, thank you. Yeah, just real quick, I was curious what your thoughts were on why the portions of the standardized waveform A and D tend not to denote the total charge transfer from that portion of the stroke. I know it would seem as though those could be calculated and annotated, but do you know pedagogically why that's not typically conveyed?
Not off the top of my head. Cody Weber, are you online?
I am, Karen, and I heard that one. So They typically refer to the charge transfer in the continued currents associated with lightning component B and C for those long hang-on environments. And so that's where they typically track the charge. And there's one of the figures of merit of component A and D is the action integral that they use as the integration of the lightning current waveform, but they typically don't use that as a typical thing to check when they're doing their lightning injection as well. So I don't have the exact reason why they don't track charge for lightning components A and D, but it sounds like you may be aware that they do it for B and C.
Correct. Yeah. Thanks very much for that answer.
Great. Anyone else?
Yes, this is Jun. I heard some unfamiliar terminology, so I understand that the open circuit voltage, short circuit current, but when you say open circuit pin voltage, short circuit pin current, is that the pin has some special meaning or connotation?
No, I believe it is the pins that are located in that basically.
Just mean the terminals?
Yep.
Okay. Okay. Thank you so much. That's it. Oh, by the way, I work for Ford too.
Oh, great. Yes.
Thank you. Very interesting presentation. Thank you.
Thank you.
You have another question?
I have an anecdotal one.
Okay, Joe.
So we've all been told to get out of the water when the lightning's coming. Why don't the fish jump out? How about ducks and stuff? So I was wondering, honestly, like you see lightning storms out on the beach, out in the salt water and stuff like that. But you don't see a bunch of animals washing up on the shore afterwards. And I just think that it's probably a low impedance or, the skin effect, whatever. It just spreads out the charge so much that there's not real current there. Has anybody thought about that?
Yeah, I think you're exactly right. That basically it gets spread out so much through the volume that it doesn't affect any individual creature. Like there's just not that much impedance difference between,
Right.
or, voltage drop from one side of a fish to another side of a fish.
Mm-hmm. Well, or yeah, you would think that if you're under it, you're like a fish, or, hey, a duck with part of it in the water and part out, like I would be in the pool. But so you're saying Mom was wrong.
Well, I still personally wouldn't go swimming.
I just really think it's one of those funny things that if you really think, it's usually one of the things I bring up at the bar. and I don't get any good answers.
Well, Joe, if you're the highest object, though, on the sea, you're going to be hit, though. That's the issue. Well, you see ships. You see, like Archibald showed me a picture of his, he had his sailboat. Right. Get hit, because it's got that mast sticking way up. But nothing happened to it. So, that's a good point, because there's ships out there, exposed to stuff all the time. Now, I'm just talking about it, they go, if they're metallic or whatever, they can conduct through pretty well. But then you got the composite ships, things like that.
When we sailed in storms on the Great Lakes, we usually had cables that ran into the water to divert the lightning strikes if there were any.
Right, because you can see exactly another example of that field concentration at the top of mass, and that's that classic St. Elmo's fire, right? Yeah. You get that corona effect right at the top of mass in those situations, and it definitely makes you think twice about messing with the electromagnetic fields there.
So that leads me to my question. Can you just talk a little bit about lightning rods and how they work on buildings?
Cody, do you want to take that one?
Sure. So it's the same kind of thing you're just talking about. If you can have a greater field concentration at a particular point, then you can better control where the lightning will strike. And then so if you have a lightning rod positioned in a way that is most likely to take the strike, you can have down conductors or a network beneath it that can safely mitigate that lightning threat and conduct it to ground from there. And so if you let lightning strike wherever it wants, you can end up with a bad day. And if you can control where lightning goes, you're much better off mitigation wise. And that's often what they do in aircraft design too, is that they put lightning conduction networks specifically designed into the airplane to control lightning currents from the extremity points.
Yeah, I knew I was running a little long, but I actually took out a slide that showed, for instance, how you can have these lightning diverter strips that specifically protect radomes by giving lightning currents a path that that they can safely conduct back to the fuselage instead of just dissipating all their energy in the fiberglass.
So there's some things in the chat window too.
Oh yeah.
They want to know if your slides will be available. Can I post those? Would that be okay?
Yes, definitely.
Okay, and then also I'm recording this, and I will put the link to this recording with the slides on the announcement page when I get that done. It might be a couple of days before I get that all put together.
Great, thank you.
And then Malcolm has a comment. If you're a ham radio person with a vertical, it's called a corona ball and has a surface area more than a sharp point to be able to spread out the current. So it's a comment from Malcolm.
Yep.
Okay.
I've definitely seen those.
Okay. Any other questions?
Yeah, I'm kind of curious about something here. This has to do with the simulation. Because I'm a little bit familiar with this. How much time does it take to build up a model that has reasonable fidelity like that? That looked pretty intense. And is that something you guys do, or is that something like the aircraft manufacturers do?
So, and again, Cody can speak to this a little bit more than I can, because I believe he was involved in this exact effort. But you bring in the CAD from the aircraft manufacturer, but then a lot of times you're doing the cable specification by hand. Now with EMA 3D, that time, because we've got a very mature GUI for doing that, that time can be reduced from, you know, sort of man years to more like in the weeks and months kind of time frame. But yeah, it's definitely not an overnight process.
And so when you're importing CAD models from like the skins and all that, I take it that that process really goes that smooth, because I've seen other situations where you try to import data from from regular mechanical CAD packages and try to bring them into like electromagnetic simulation software, and you literally spend hours fixing up things because they don't mesh correctly or what have you.
Right, and I won't say that we're immune from that, but again, with the FDTD solver, because your mesh can be, you know, relatively on the coarse side, not as much cleaning is sometimes required as with some other packages.
And I'll just offer one other point. It took me about 3 months to build that model that you see there, and along the way, there were small exploratory simulations, because when you have analysis, one of the greatest benefits is that you can do parameter studies. You can do changes in design and understand how it will impact your results. And so as we started to build the model, there was a lot of interest in these small side studies. Well, what happens here? What happens here? What if we change this design? And so to put the model together was about 3 months. But when you incorporate all those side studies and get the analysis point to the end, it's over a year process for that. So there's really a ton of benefit to doing those size studies as well.
Yeah, I can agree. Once you've got the model built, you know, now one of the big things that I always see as a major issue is that dreaded C word, correlation. In other words, yeah, you can build up a model in a computer, but if the model doesn't have sufficient fidelity to predict real world responses, and I know a little bit about this because I work doing antenna testing, So this is a, there's always the, well, why can't we just simulate this instead of like running it on the antenna range or in the in the spherical near field chamber? And it's like, well, if you don't have good enough, you don't have a sufficient fidelity model, you don't get good correlation between what the simulation produces and what the and what the real world measurements are. And it looks like you guys, 6 dB fidelity is considered, well, I guess for something like this, I would probably think that would be pretty damn good too. But just kind of curious as to how you built up that confidence in the simulation versus real world measurements.
Karen, if you don't mind, I'd like to speak to this.
Please do.
That's a topic near and dear to my heart. I've been doing simulations for almost 2 decades now, and that's always the question that comes up. And Karen, she mentioned the quote earlier today to me, and it ones that rings true, that when people doing the test, everybody believes the test but the tester, and people doing simulation, nobody believes the simulation but the simulation person. And when we're trying to build up this confidence, there's 3 different approaches that we can take to it. And one of them is sort of a predictive comparison, like we try to do here, and get in a certain range of agreement with them in a dB sense. And in 6 dB, in my opinion, is also very good. And in the antenna world, that probably is not. But when you're talking about lightning transient response, it tends to be. And then there's an approach that you can take is a conservative view response. And so that if you can do different types of analysis and some sensitivity characterization and convince the authorities that you're on the conservative side, then they tend to agree with it a bit better than if you just go in and try and do a one-to-one comparison with points. So basically, when we go and do this analysis, we do these side studies and sensitivity analysis to try and support the idea that we can do conservative estimations of them for certification purposes. Now, you can't just have a model that is conservative everywhere. And so it takes multiple iterations of simulations to try and establish that argument. And it's not necessarily an easy thing to do. And I'm actually on the AE2 Lightning Committee, and we're updating the standards for ARP 5415, which is the indirect effects document, and the new one, which is the 6205 fuel tank ignition prevention one. And simulation use in both of those areas is growing greatly. And as a result, there's going to be a spin-off document in the next few years for simulation for certification purposes. And we're going to really try and pin down processes and techniques to establish margins on simulations that would be more acceptable for certification purposes. And we're really getting good contributions from many OEMs and the authorities as well on that. So it's gaining traction, and it's still a couple years away, but it's a very interesting point.
No, I would agree. I mean, simulation, if it works well, I mean, it's a big, it's a big force multiplier, I guess, if you want to call it that, because you can literally save, in the case of an aircraft, probably saving millions of dollars in time. But I guess it's probably, when you start, the first time this was done, that was probably very painful, because you had to build up you had to take the CAD models, and then it's not just drawings. Now you have to assign material properties to everything to make this work right, especially if you're looking for how the current density, what the current density is in various pieces of the structure and all that. I assume that, once you've done this once or twice, then the aircraft manufacturers can kind of like have a library of sorts that they know how to build this up. But yeah, it seems like the initial work is what really would be the killer here.
It sounds like you've been through it before. Yeah, you bring up some very good points on the topic, and it does, it takes an eye for it and some experience in order to put together a model like this. And some people just choose to avoid it altogether, but they can still have value from simulations and doing some focused areas, or doing submodels or more canonical, and get design guidance in that way. But yeah, our hope is, and our push, and what we do at EMA, is to encourage the simulation use all over. And it does seem to be going that way more and more. And so having strategies and techniques to confirm the accuracy in an acceptable way is something that we're really, we're fighting for.
Hey, Cody, I have to the materials question. So I'm not as familiar with the Embraer overall monocoque structure. probably more aluminum. But with the varying levels of conductance available from our composite, lightning problem in different ways, how do you plan to approach that regarding material power?
Mark, I'm sorry to interrupt. Mark, I'm sorry to interrupt. It sounds like a very good question, but your audio is breaking up. I'm not sure if anybody else could hear that clearly.
No, unfortunately, I was getting garbled.
Okay, I'm sorry. Can you try again, please?
Yeah, you can hear me now. If you can't,
Yeah, you might want to take that one offline.
Yeah, still.
No sweat.
Yeah, I'm happy to discuss it, and any questions are welcome.
Try to put it in the chat.
Sounded like one too long for the chat.
So if there's no more questions at this time, I'd like to move on to our contest, or our drawing, I should say.
Sounds good. Thanks, Scott.
Okay. Before we do that, though, by using your reaction button in the bottom there, I'd like to, just by a show of hands, use the hand up or thumbs up, I don't care, something like this. I'd like to see how many people have actually observed ball lightning in their lifetime. I'd like to do a quick survey. So if you've ever observed ball lightning, throw your thumb up. I'm just curious. I see only one other one so far. Two.
My grandmother did, but not myself.
I have actually. So I just wondered if anybody else has ever observed this. So I think there was, what, 3 people out of this group, which is pretty good. Yeah, my story is I was coming home from golf after work. I used to work up at Eaton in Southfield, and I was coming home. It was, you know, during the end of the day, and there was a thunderstorm in the area. And I was up on that big bridge over I-696, 96, and 275 all come together. And I was on the bridge southbound, and all of a sudden, you know, lightning struck, and there was a ball of lightning at least 6 feet in diameter, just sat there on the ground for several seconds on the side of the highway. So just the most amazing thing I've ever seen. Oh yeah.
Nice.
Yeah. Okay. So this time, what we're going to do is instead of doing a quiz like we did last time, it took a long time. We're going to do something a little different. What we did is we took everybody who registered for the meeting and we sorted them in order of registration time and date. We put them in a list, and then we used a Google random number generator to pick from our list. So you must be present to win. So when I call your name, unmute yourself and speak up. And if I don't hear anybody, we'll go to the next one. So the first one is for $100. I believe it's a gift certificate or a gift card or something. Dan, what is it exactly?
Amazon gift card.
$100 Amazon gift card. So the first one we drew is Ron Messier. Ron, are you still on the line?
Yes, I'm online, Scott.
Excellent.
All right.
Ron,
Thank you.
You were lucky number 7, which put you for the first one.
What a day. Thank you.
Okay. Congratulations.
Yeah, thanks, Kevin. Thanks, Dan. Thanks, Cody.
Thanks for hanging in there, Ron.
Sure. It was very interesting. Thank you.
The second one is for a $75 Amazon gift card. And the second number we drew was 28, and that is David Evans. David, are you still online?
Oh, yes, I am. Yeah, thank you.
Excellent. Okay, David. So write that down, Dan. I'm going to be sending you the mailing list, Dan.
Okay, I need the email addresses. Yeah, that'd be
You'll
good.
get all that. You'll just write down David Evans. You can pick it out of the list when I send it.
I got it.
Third prize is for $50. And that is number 37 in the list is E. Avila, A-V-I-L-A. Are you here? First initial E, Avila. Please unmute yourself. You got 5 seconds. We're gonna go to the next one if not. Okay, the next one we drew is number 32, Jamal Shafali. Jamal.
Jamal Shafi. Yeah, I'm here.
Okay, so Jamal, you won a $50 Amazon gift card, and Dan will take care of that one. So I'm going to
Thank you.
circle the
Welcome.
winners here. Thank you, everybody. And that went a lot quicker than last time. I hope you liked that. Those that won. Let's see if I had any closing comments here. The only thing is, yeah, we will have this recording and all the slides available, and I'll email that back out to the entire list. So thank you again, everybody. Thank you very much. And just a reminder that 1 week from today, there is a meeting at, I believe it's 11 a.m. It's a joint meeting. Quite a few chapters are on this one. It's through ETS Linger, and you should have gotten an email from me. So at this time, I guess we will sign off if there's any further comments.
Great. Thank you very much, everyone.
Thanks, everyone.
Great presentation. Thanks.
Thank you, everyone. Great presentation, Karen.
Thanks.